Our chapter is moving charges and magnetism. Okay, so we start our discussion. The chapter's discussion starts actually with Oster's experiment. Do you remember Oster's experiment? Yeah, Oster's experiment. So we will discuss this. There's nothing more to write, but whatever are the takeaway points, we will discuss on those. Oster's experiment. Name of the person was Hans Christian Oster, and where the Christian word is written with K because he was a Danish guy. Okay, so what Oster did, Oster's experiment is also one sort of a serendipity. Actually, Oster was studying something called heating effect of current, and suddenly he observed that magnetic compass is deflecting. So you want to study something and you find out something that which actually gives you far more important findings. So the experiment setup is very simple. So a current carrying conductor is taken. This is a current carrying conductor, and this current carrying conductor is connected to a key, and then we have what do you call a EMF source, and so the current will be flowing. This is my conductor. Okay, this is my conductor. So as soon as he turned this on, he brought a magnetic compass in his vicinity. Actually, the magnetic compass was in his vicinity. So let's say that the magnetic compass, this is the direction of north and this is the direction of south. The magnetic compass will usually show point towards north and south. Okay. So when Hans Christian Oster accidentally actually pressed, this circuit is turned on, this compass needle undergoes a deflection. Okay, undergoes a deflection, and the deflection is sustained till the circuit is turned on. And once the circuit is turned off, you need to remember just these three things for any sort of 1-mark question. There is a deflection in the compass needle as soon as the circuit is turned on. The deflection sustains as long as the circuit is turned on. Once the circuit is turned off, the compass goes back to the geographical north direction. Okay, so human beings will always have some sort of curiosity that what if I change the polarity? What if I change the polarity? So once the polarity was changed, he found that the deflection now happens on the opposite side. The deflection happens on the opposite side, and it's an equal amount of deflection. Again, deflection is sustained as long as the circuit is turned on, and once the circuit is turned off, the deflection is again restored back to the original position. Okay, so the first thing we saw was that there is a deflection. There is a deflection, and the deflection is when current flows. Okay, current flows through the conductor. Okay, so children, are we clear on this? The deflection will be there as long as the current flows through the conductor. If there is no current flow, the deflection is restored back and the compass points towards the geographical north and south position. Is this clear? Second, if you change the polarity, the second thing that we saw was change of polarity. So just remember these points, change of polarity. So if you change the polarity, the deflection is on opposite side. Same story. Okay, same story. Now the third thing he saw, that if the current magnitude is increased, the deflection also increases. The deflection also increases. If we increase the current's polarity, so the current strength of the current, you can keep a rheostat out here. Have you seen a rheostat in a lab? The variable resistance, yeah. That's a very dangerous item when you do AC testing. Okay, I will tell you some stories about that also. So you can actually have a rheostat, let a less current flow through it, then allow more current to flow through it. So we see that the deflection also increases, which tells you, we'll discuss about all these things. And the fourth one is that the compass, if the compass is brought close to wire, okay, so on the fourth one, what we are trying to say is like this. See, the intensity of the current is maintained, the polarity is kept same. Now we are shifting the compass. As you move away from the wire, the deflection, compass close to the wire, so the deflection will be more, and vice versa. Children, try to note these points and elaborate your understanding. If you have any doubt in any one of these, you can actually ask me. Have you understood all the points? You should actually elaborate all the points. Deflection. So the first thing is whenever current flows through a conductor, a compass in its vicinity deflects from the usual north-south position. The deflection is sustained as long as current flows in the circuit. As soon as current ceases to flow, the deflection is restored back. If the polarity of the current is changed, then the deflection is also swapped to the other side, right? Then, if the strength of the current is increased, the deflection also increases. Fourth, the magnetic compass's vicinity is inversely proportional to the deflection. More it is closer to the wire, when the current is flowing through it, the deflection will be more. This is directly proportional. Yeah, directly proportional. The more closer you are, the more will be the right. This makes us feel that why did this compass actually deflect? The compass under a normal condition would be sensing what? Just the Earth's magnetic field. That means an additional magnetic field got created in and around in the vicinity of the compass, which made him deflect his position from the usual south-north orientation. Have you understood? So from there, Hans Christian Ørsted said, current carrying conductor behaves like a magnet, and the current carrying conductor creates a magnetic field around it. Creates a magnetic field. We'll be talking about field a little bit later. So a current carrying conductor creates a magnetic field around it, or a current carrying conductor behaves like a magnet. Now this is what you have been studying in grade 10. But now since you are in grade 12, let's add a little bit of more caveat to that statement, okay? And that would be very important for the sections that we will study. I said a current carrying wire or a current carrying conductor. Shall I just revise my words and I say, moving charges creates a magnetic field, yes or no? That's why the chapter's name is Moving Charges and Magnetism. What is current? Current is the flow of charges through the cross section of a conductor. When you were in grade 10, you used to say that a current carrying wire behaves like a magnet. Now I'm saying that moving charges creates a magnetic field in and around it. Fair enough statement, right? Okay. So then comes is, we need to understand the direction of the magnetic field. But this magnetic field, we will be diving deeper. Magnetic field. What is the direction of the magnetic field? The direction of the magnetic field is given by magnetism. Chapter is all about palm, fingers, and hands. Right hand thumb rule. Right hand thumb rule. Position the thumb of your right hand in such a manner that it is pointing towards the direction of the flow of the current. So this is the position of the thumb. And then the thumb is positioned like this, and curl your fingers in such a way that they will actually show you what is the direction of the magnetic field. So in this case, the magnetic field will be in this direction, which is counterclockwise if the current is actually flowing in the upward direction. I hope it is clear. If you swap the direction of the current right on the southward direction, then my fingers will be curling in clockwise manner. And this is precisely the reason why the compass was deflecting in the opposite direction when we were actually changing the polarity of the current. Is this understood? Okay. Then in grade 10, we also said we had a concept called magnetic lines of force. The magnetic lines of force are actually imaginary lines which tell you how the magnetic field behaves in and around. So a magnetic field line of force is what? It always originates from the North Pole and terminates at the South Pole. They will be more concentrated near the poles, less concentrated near the halfway side. And if you see a region, let's say this is a bar magnet, okay, and this is north and this is south, I would find my magnetic lines of force will always be in this manner, right? And if you actually analyze or sample a space out here, you would see more number of lines per unit area, which shows that there is a greater concentration of the magnetic field. Strength is much more. But whereas if you take the same sample of area, maybe only one line and a partial line is passing through this. No two lines of force cross over each other. If you want to know the direction of magnetic field at any point, so Take the point, look at the arrow and draw a tangent and see which side the tangent is pointing. No two lines cross over, because if two magnetic field lines used to cross over, say this is line L and this is line M, then for L I will have a direction here, for M I will have a direction here, means one point having two directions, which is not possible. Therefore magnetic field lines don't cross each other. This was actually also proved by something which is discussed in your topic, which is known as the iron filling experiment. I hope you know this. Iron filling experiment. What is the iron filling experiment? Take a drawing board, like a board, not that much thick, and put a bar magnet right below it, and put a A4 size paper on it. Pin the A4 size paper and sprinkle powdered iron on that. The powdered iron will exactly take this shape of this butterfly, which shows that the magnetic field lines are in this order. And how do you trace these magnetic field lines? I think State Board has this experiment. CBSE doesn't have. Take a magnetic compass. You put your magnetic compass out here, so it will be pointing here. Then put a dot here. Put another. Then it will put here. Then put another dot. It will go here. So we trace the magnetic field lines. Till here, fine. Like, let's some more symbols. Okay, some more symbols. Shelling which happens across the border, LOC, you keep on hearing. Have you seen how a shell looks like? A shell, I can't draw 3D, but I'll try to. So the shell will always have an arrowhead like this. Do you agree? And on the back side, you will have something like the feather cross shell, mortar shells, or arrows. If you see, they will always have something like this at the back, the fins. So this is very important for us to understand magnetic direction. So let's say there is a paper, or say my screen out here, and I want to say that current is coming out of the paper. Current is coming out of the paper. So all those parameters are seen like an arrow, right? If you see this, now take this. If you see the front view from your side, what do you see? You will see a dot and this circle. You will be seeing basically like this. My stylus, you will be seeing like this. Do you agree? That means the stylus is now coming out of me. So any current coming out of a paper is represented like this. Same would be for a magnetic field also. Coming out of the paper. Do you agree? And now say this is that mortar shell and it is going inside me. Then what do you see from the back? You will see that cross fin. So any current that is going inside, we would see it like this. Means the arrow has gone inside the board. These two you should remember, because whenever those Fleming's rules and all comes up, we will need those. Fine. So let me have a quick revision. Oster's experiment and findings. Are we fine? Iron filling experiment, we are fine. Symbols for current going into paper, current coming outside paper, and the right hand thumb rule. Are you fine with the right hand thumb rule? Right, fantastic. Brings you into your next section, which is magnetic fields. We'll be talking about magnetic fields, and the topic is all about source and field. First, we will be talking about field. Field, just field. Field. So, field as a definition, see, let me just read it. It becomes so easy. Region around an object. Field. Region around an object where it can exert a force on another object without touching it. Earth's gravitational field. Now let me put that definition. This is Earth. This is Earth. And there is a region around the Earth where it can, now this is an object. Region around an object where it can exert a force on another object without touching it. That is called field. Such a field can be gravitational field. Such a field can be whatever you have studied so far. Electrostatic field. Such a field can also be a magnetic field. Right? And if you want to hear a coarse language for this, all these dadas and all which are there, heroes और दादागिरी जो करते हैं ना, So a Dada also has a field around himself where you will be afraid to walk in front of him because it is his area and his field, where without touching you also he can exert a force on you. Clear? Right. So a charged object, you can write it down, a region around an object where it exerts a force on another object without touching it. For example, a charged object will give you an electric field, and a magnetic or a current carrying wire. Right, we did not say that. So I can also say like this, see, there is a wire which is carrying a current. It will also have a field around it because it is a magnet. So you can write a charge has a magnetic field, a celestial body has a gravitational field, a magnet or a current carrying wire has magnetic field. Achha, what is the difference here? Look, this one and this one. That is how the story of this chapter goes. This is stationary. And here the cues are, they have to move. So always remember, whenever you will be calculating magnetic field numerically, velocity will be a part of the story. No velocity means no current. No current means no magnet. Simple. Right? So, couple of illustrations. So what is the electric field? Let's look at the electric field back once again in vector form. Electric field due to a charge Q is given by, electric field is the force per unit charge, Q by 4 pi epsilon naught, and then I will 4 pi epsilon naught. I will put a r square at a distance r due to a charge Q. Now since this is vector, I should put a r cap out here. R cap is the direction, and if you show r cap in terms of r, then this one will become cube. I hope you know that. Because what is a unit vector? A unit vector is the vector which has been stripped out of its absolute value. So if you put a r out here, r arrow, then this becomes r cube, right? Now this is an electric field. Now what do you see in this electric field? If the charge goes up, value of Q goes up, what is the impact on the electric field? The electric field also goes up. If the R goes up, then the E's value will reduce. And if the R reduces, the E's value will spike up. Is this understood? Fine. Now, in this electric field, so we have Q now. Q has got an electric field around it. Let's say this is a positive charge. I bring another charge Q out here, usually positive in nature. Then I can say that there is a force experienced by this charge, which is given by QE. And the force will be always in the direction of the electric field. If the brought in charge was a positive charge, it will move away. And if the brought in charge was a negative charge, it will be attracted because your central charge is you have taken as positive. So this is also understood with you. Now, electric field. Now, this still the concept of electric field, and this field is called a real field. It's real. You can't see it, but it is real. Why? Number one, exerts force, right? Transfers momentum and can also transfer energy. Therefore, it's a real field, right? Keep this in mind, these three things. An electric field exerts force, an electric field can transfer energy, and an electric field can also transfer momentum. Force is, what is force? Force, end of the day, is change in momentum per unit time. And whenever you have problem force, force is always dp by dt. What is dp? dp is nothing but final momentum minus initial momentum divided by t, change in time, mass constant, v minus u by t, which is equal to ma. v minus u by t is m. Real means there is a real field which exists. You can feel it, you can see it. The existence is real. It's not something that we are talking like magnetic field lines is hypothetical lines that you created for the benefit of you to understand the geometry of magnetic field. No such field lines exist. That was your hypothesis, but it is actually like a vector. You give it for your ray of light. There's no ray of light. Ray of light helps you to support ray optics, but this one is not like that. You can't see it, but there is a field, and this field can actually transfer energy, transfer momentum, and can also transfer and can also exert force. See, this chapter, as we are discussing, please understand, magnetism and electricity were actually considered to be completely two diverse topics. There was no connection in between both. Take yourself back to some 1600 and 1700s. Do you expect anything of magnetism and electricity to be in common? No, you don't know anything about that. Till Hans Christian Ørsted gave you the first finding that there is a connection, that a current carrying wire behaves like a magnet. And later on, as the time when Faraday's laws and all comes of electromagnetic induction. So this chapter talks all about current as an input, you are getting magnetism as an output. Later we will study magnetism as an input, do you get current as an output? Man's brain starts thinking like that. So there was one more person whom we study in electromagnetism a lot, whose name is James Clerk Maxwell. So Maxwell later said, and this electric field, you know, it does not pop out straight away. It takes time to establish. There is a propagation time also. This is studied later by Maxwell when he says this propagation happens in the form of electromagnetic waves. So therefore, we write, field does not exist everywhere. Electric field does not exist everywhere, does not appear everywhere. It takes time to spread. It takes time to spread. This idea was developed by Michael Faraday and explained mathematically by James Clerk Maxwell later. Electric field does not appear everywhere. Just touched it. Yeah, electric field does not appear everywhere. It takes time to. This concept of electric field was Michael Faraday's. Mathematical model was given by Clerk Maxwell. Okay. Then further we know, we have studied about superposition theorem, where we say if there are many electric fields, this is a vector quantity, it is actually equal to the vector sum of each individual electric field. So far chapter is all easy for us. Clear? So time for us now to dive into magnetic field. Electric field enough we have studied. Now magnetic field. Just go by notes and read it in this manner, you will have no issues. Number one, charges. And I would say stationary. Morning when you go to drop your kids, ask them there only, what is the spelling of this eraser and what is the spelling of the planet? You'll see how many correct answers you will get. Stationary and stationary. Okay, charges stationary will produce what is known as electric field. What happened? Today you were driven by your mom, you missed bus, right? Hey, when you crossed in front of Pebble City, at that time the bus had already left. You must have boarded it a little bit ahead. Where the bus was parked, my eyes never see something wrong. The DPS bus moved out. After that, you came in scooter with your mom. You have boarded the bus a little bit ahead, not at the usual position. What may be? It happened today morning and you're saying maybe? Yeah. Oh, that is something different. And your share of all your, those doggy potty, what you eat in the morning, that was eaten by Samarth. I don't see wrong. Moving charges. Moving charges will create magnetism. And it's nothing new that you are learning, because you just learned about Hans Christian Ørsted experiment where he said a current carrying wire behaves like a magnet. So current is what? Flow of charges, moving charges, and the moving charges are going to create your magnetic field. The magnetic field is magnetism nahi, magnetic field. Magnetic field. And the magnetic field is always denoted by B with an arrow on its head. So this is a vector quantity. A magnetic field is a vector quantity. Now write down some of the properties of magnetic field. Okay, write down some of the properties. Property number 1. And whatever you are writing is nothing new. It exists in space. It exists in space. So please write that down. That's a property. Magnetic field exists in space. Number 2, has both magnitude and direction. Has both magnitude and direction. Why? Because it's a vector quantity. Now, a very nice thing I'll say. Okay. Now look at this. This is a magnetic field. So the magnetic field will always surround a magnetic substance. Right? This is a magnetic field. Who can create a magnetic field? A magnet, or rather I'll say a magnetic substance. So this magnetic substance can be a natural magnet which you found, and magnets are always from the ores of iron, cobalt and nickel. Remember that, okay? It can be from iron, cobalt or nickel, okay? Iron, cobalt or nickel. It can be either of three, or current carrying wire. That is also a magnet. So with a current carrying wire, no, don't write. The current carrying wire means an electromagnet, which we studied in grade 10. Permanent magnets or electromagnet. So this magnetic field, acha, tell me one thing. Gravitational field exerts force on whom? Think in terms of physics. I am Earth. I exert force on whom? On someone who has mass. Arey bacha, the gravitational force is what? G m1 m2 by r square. If you don't have this, then you don't feel the gravitational pull, right? See how you should study. The electric field exerts force on whom? Charge. Electric field will exert force on charge. If I am walking in an electric field and I don't have any net charge on my body, do I experience any pull? No. A proton with a very negligible mass, imagine the mass of a proton is there, or an electron, very negligible mass, is moving around Saturn. It does not experience any force because Saturn is going to pull someone who has got a mass with it. So now come to the question here. This is going to pull whom? Magnets. So magnets means one is it can pull a magnetic substance. Another thing you are not answering is it can attract moving charges. Because a moving charge produces current. Now imagine yourself, children, this is so interesting. I have an electric field, I have a magnetic field. There is a single charge sitting here. That charge will be attracted by only this field because the electrostatic field can attract the charge. The magnetic field will not attract that charge. Let's change the question now. That charge is moving. Who will attract that charge? Both. Electric field ke liye he is still a charge. And for the magnetic field, he is a magnet. So interesting, right? And that is what will give rise to something which is known as Lorentz force, which we will study today itself. Okay, there was a person who Heinrich Lorentz, I think. Okay, so Lorentz gave a force which was known as Lorentz force. So write down your next property: can exert force on magnetic substances and moving charges. Magnetic substances and moving charges. See, all these can come in very 1 mark type of question. That a moving charge will see a force from both. Okay, our next point. Magnetic field follows superposition principle. So you can write down B net is equal to B1 plus B2 plus B3 dot 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 in vector form. Okay, B net vector is equal to B1 plus B2 plus B3. B1 plus B2 plus B3 in vector form, right? No issues, children, so far? So time for us to also see a quick differentiation between an electric field and a magnetic field, right? Make a T orientation like this and write down these points also. E versus B. Point number 1 on the left side, produced by electric charges. Produced by electric charges. So on the right hand side, what should you write? Produced by moving charges. Hey, she was saying produced by magnetic charges. Produced by moving charges. Did you play that game in childhood? We used to play what all flies and what all doesn't fly. You have to put your finger on the table. Crow, pig, then pig also flies. Okay, done. Then you can write symbol. You can write the symbols. One is E, one is B. Already you have written. So you can write the third point. Third point on the left will be action on any acts on any charge. Acts on any charge. So please understand, positive, negative, moving, stationary, the electric field is always going to haunt a charge. Acts on any charge. Whereas on the right side, you will write acts on moving charges and magnetic substances. Acts on moving charges and magnetic substances. Clear? Write vector on both and follow superposition for both. So the next 2 points, vector on this side, vector on that side. This is a vector quantity, that is also a vector quantity. Done. Our next topic is magnetic force and Lorentz force. Magnetic force and Lorentz, Lorentz, Lorentz force. Magnetic force. Just understand the concept first. It will be easy for you. Okay. There is a charge Q which is placed in space and is moving with a velocity v. Right? There is a charge Q which is moving with a velocity v. Why did I bring the concept of moving with a velocity v? If it doesn't move, how does this fellow will not be born? Right? And this charge is placed in a region. This is placed in a region where you have called electric field and you also have magnetic field, the maximum complex that you can think. This charge is moving with a velocity and the charge is placed in a field, in a zone or a region where you have a magnetic field as well you have a electric field. Now what happens? This charge is going to experience a force, and this force will be contributed by both the fields, the electric field as well as the magnetic field. Do you agree? Okay. If you would like to quantify that force is given by Q, the electric field plus the cross product of V and B. Cross product. We will come to this later. Right? So QE was already known to you from the previous chapters. QE is the contribution by the electric field. This was known to us. And QVB, Q is a scalar. Huh? This is a cross product. This is a scalar. So it's a scalar multiple of a cross product. Then this force is actually called Lorentz force. Lorentz force. And Lorentz force is actually the sum total of the electric field force, or the force due to electric field, plus force due to magnetic field. Have you understood? So what is the thin line difference between magnetic force and Lorentz force? Lorentz force is the force which takes into account that if there is an electric field, now it's very interesting. See, if this was placed in a zone where there was no electric field, Lorentz force doesn't come into play. At that time, there is only magnetic force, because Lorentz force is the sum of both the electric force and the magnetic force. The electric force component would have been zero. Is this understood? Okay. So we now dive a little bit deeper. Have you written down this part? And you have already studied that this force will only act on stationary charge plus moving charge. This will act only on moving charge. So, complicating the question, a stationary charge is kept in a region where both the fields exist. Will it experience Lorentz force? Yes. Electric field only eyes you as a culprit. They will eye you as a prey if you are a charge. You move, you don't move, the electric field is like a tiger and you are like a deer. Okay? Have we noted that down? Okay. So our idea is to study about magnetic force. So let's dive down a little bit deeper. So electric force is given by QE. We will not concentrate on this. We will concentrate on the magnetic force. The magnetic force is Q into V cross B. So when you say V cross B, children, are you fine with cross product of two vectors? Sure. You know everything. Okay, let's see. Two vectors, a vector A and a vector B, A and B. A cross B will always give birth to another vector who is C. Remember that. C is such that, let's look at what is the magnitude of C. The magnitude of C is mod A mod of B into sine of the angle between them, theta, the smaller angle. How about the direction? C is a vector which will always be perpendicular to the plane containing both the vectors, parent vectors. So what is that perpendicular? Now my screen is the plane which contains both A and B. Agreed? Therefore C should be either coming out of the screen or going inside the screen. But sir, with what is C? Again, right hand thumb rule. A cross B, that means A is moving towards B. Put your right hand palm on A and try to move it to B. At that position, the thumb is showing outside. So C will be in this direction coming out. Had you done B cross A, the thumb is like this. B comes towards A. The thumb goes inside. Then B cross A will have a opposite direction. Then B cross A, suppose if I do B cross A will give me an anti-vector which is negative C vector. Negative C vector means goes this side. That means cross product is not commutative. Got it? Dot product is commutative because dot product always gives birth to a scalar. Cross product is going to give birth to a vector. So it will have a direction component associated with it. Have you understood? Clear? So let's go back here. So if we see magnetic force, so this magnetic force depends upon, number one, what is the magnitude of Q? It will depend on the magnitude of Q. Greater the value of Q, greater will be the magnetic field. This is magnetic force. Greater will be the magnetic force. Second, it will also depend upon the mag of V. Then it will also depend upon the mag of B. Then it will also depend upon θ theta. Theta is the angle between B and V. Is this clear, bacha? Have you understood? Now the question comes, sir, Q was a positive charge. Q, acha, understand. Magnetic force is going to exert a force only, a magnetic field is going to exert a magnetic force on a moving charge. This moving charge can be positive or negative. Do you agree or not? My Q is actually moving with a velocity V, but the Q itself may be positive in nature or negative in nature. How do I address that? You will always address V cross B. So what is V cross B? V cross B is coming out of, that is the sign of positive Q. If the positive Q is there, then V cross B is coming this side. And if your charge is negative, then it will be V cross B in the opposite direction. So we don't say it as B cross V, we will still say V cross B. V cross B, standard V cross B is always with a positive Q. If your charge is negative, change the direction opposite to it. Clear? No. The question is, sir, how do you interpret this expression? I interpret this expression as a positive charge moving with a velocity V and B. Can you do V cross B? You can with your palm and finger, and you get a direction. That is the direction if the charge would have been positive. If the charge is negative, you just change the direction. Yeah, you just say. So in a very small nutshell, so it's like that. You will always do V cross B, Victor cross Bob. Whatever you get, charge is positive. If the charge is negative, change the direction. That's all. Clear? So now, next. Number 1, maximum magnetic force. Now let's see what is the mag of this force. The mag of this force is Q V B sine theta. Do you agree or not? Magnitude of this force is Q V B sine theta. What is the maximum? For maximum, sine theta's value should be 1. Sir, who told you all these things? Array, sine graph always has the maximum value of 1 and the minimum value of -1. In order for this to be maximum, sine theta should be 1. And sine theta is equal to 1 means the theta's value is 90 degree, which means V as a vector should be perpendicular to B. Charge should move. So very interesting. See, magnetic field is in this direction. Charge should move in this direction. Then only the magnetic force is maximum. Something like this. This is in this direction, it has to move in this direction. Actually, when you study electromagnetic waves, you'll see like this. One is this, and you have to move 90 degree to the direction of both. You can actually feel it. Right. So let's see what is minimum. Minimum magnetic force. So minimum magnetic force will be when theta is equal to 0 degree or 180 degree, then the magnetic force ceases to exist. If you are moving along the direction, U means you are a charge. Whether you are positive or negative, if you move along the direction of the magnetic field or you are moving opposite to the direction of the magnetic field, in either case you are creating a sine 0 or a sine pi and its value is 0. Clear? Excellent. Sharp children. Okay. So now we need to get into the US Senate person and his brand, Tesla. Tesla is the unit for magnetic field. So let's see. The magnetic force F, okay, the magnetic force F is given by Q V cross B. Do you agree or not? Right. So if you want to separate B separately, it's a F over a Q into, don't take it as a cross product, into V, just like that. Right? That means it's a Newton divided by a Coulomb over meter per second. Do you agree or not? That means it is a Newton second divided by Coulomb meter. In such a case, the unit SI unit of B is said to be 1 Tesla, or written as 1T. 1T. So what is 1 Tesla? What is 1 Tesla? 1 Tesla is the strength of that magnetic field which exerts a force of 1 Newton on a charge of 1 coulomb when it is moving perpendicular to the magnetic field with a velocity of 1 meter per second. मजो आयो? अगर एक चार्ज 1 कूलम का एक मैग्नेटिक फील्ड के डायरेक्शन से परपेंडिकुलरली 1 मीटर प्रति सेकंड की रफ्तार से भागता है, तो उसके ऊपर जो फोर्स लगेगा वो है 1 न्यूटन, और उस वक्त उस मैग्नेटिक फील्ड का वैल्यू होता है 1 टेस्ला, 1 टेस्ला. Earth's magnetic field is 3.5 into 10 to the power minus 5 Tesla. So slowly we will see Tesla becomes a very big unit. We will use much more smaller unit. Righto, kiddos. 1 Tesla is the magnetic field that exerts a force of 1 Newton on a charge of 1 coulomb which is moving perpendicular to the magnetic field with a velocity of 1 meter per second. Okay, so our last discussion for today, only 1 more minute, and our discussion is something like, we're going to discuss about F equal to QE versus F equal to Q V cross B. Now I hope you understand this is magnetic, this is electric, sum of both is Lorentz force, right? Right. On the left hand side, let's write X on all charges. Now this is similar to electric field, because from electric field we got the electric force. So this will be X on both charges. That's the integration, huh? Why you love integration? Integration is very interesting. 7 exercises, but it will use your brain power. Okay. X on both all charges. On that side, we'll write X on moving charges. This will act only on moving charges. Okay. Now I'm no more writing magnetic substance and all, because children, the name of the chapter is moving charges and magnetism. So we're going to talk about a charge. This acts on all charges. This acts on moving charges. Next point. Now this one can change speed. Why? A force can always create an acceleration. Do you agree or not? So on the left side we will write can change speed. But if you see the other side, the magnetic force, it does not change speed, it can change the direction. Acha, now you should say, but sir, a force is always supposed to bring about an acceleration. Yes. Change in direction is also acceleration, not always change in speed. So right, can only change the direction of motion, can only change the direction of motion, and in bracket we will add a word, if only B acts. If B does not act, how can you change the direction of motion? You can't change the direction of motion. Which one? No, on a charge is always along the line joining the source charge and the test charge. So in that it will be either increase the speed or decrease the speed. Now can only change the direction of motion if only B acts. Then on the left side you write X along or opposite of E. I hope you know that. Positive charge will be opposite of along E, negative charge will be opposite of E. And what would you write in this one? What would you write in this one? You just wrote, what is the value of the force? QVB, V cross B. V cross B is a vector who is perpendicular to both V and B. So it will act perpendicular to V and B. Are you? For you guys only I drew this, na? What is this? A cross B gives birth to what? A vector C. In your case, it is V cross B. Victor cross Bob. Victor cross Bob is another vector. Somebody call whatever, and he is perpendicular to both Victor and Bob. Therefore, magnetic force is perpendicular to the direction of both this and this. That will be the reason for electromagnetic forces. So it's something like this. See, if V is going in this direction, B is going in this direction. V is the direction of current. Go back to grade 10. FBI. This is the direction of current. Where is current going? The way where charge is going. B, V, Victor. B, Bob. Fleming's left-hand rule is going to haunt you again in this chapter. Right? So we'll close today. Job done. Whatever I thought I'll teach you, I've taught you. Next class, we'll go ahead of it.